Dr. Hussein was awarded his PhD by McGill University in 2000. His research falls in the areas of energy and environment. In the energy field, he's developing novel technologies for in-situ preparation of nanoparticles, catalysts, and solvents to serve in-situ upgrading of heavy oil upgrading. He's a professor, tenured professor from the University of Calgary, the Department of Chemical and Petroleum Engineering. And he also works for the Alberta Ingenuity Center for In-situ Energy, now the Alberta Innovate Center for In-situ Energy. Thank you.
I didn't know they changed the name.
Yeah.
All right, good morning, everybody. Try to fix this first. Right, so since I'm the first speaker from the Alberta Ingenuity Center for In-situ Energy, or Alberta Innovate Center, I'll try to set the stage for the objective of the center. Okay, so according to the Canadian Association for Petroleum Producers, this is how they project the needs for petroleum in the future to come. And most of this need from 2005 on will actually be covered by unconventional oil, which is oil sands for our purposes here in Alberta. Now, oil sands can be found in surface deposits, and we use surface mining in order to collect the oil sands and then extract or separate the oil from the sand. Or they can be found in deep deposits that you're seeing here, and there are techniques to actually inject steam and then force or reduce the viscosity of the oil that is trapped within the bitumen, to be more specific, that is trapped within the oil deposits or the sand deposits, and then force it to go to a collector or a producer well, and then collect it at the surface, and then do the separation again, make sure that you get the bitumen. And then the unfortunate part is that this bitumen is very viscous, contains so many heteroatoms, and it needs upgrading before it can be used for cars and fuel for normal operations. So just few things, few different definitions. Heavy meaning that it has high density, and viscosity. Viscosity meaning it doesn't flow easily. You have to really heat it up to high temperatures in order for it to flow. And as a result, it will be difficult to transport. And it will be very difficult as well to process in the conventional refineries. That's why we need upgraders rather than refineries. And contains sulfur, as I said, and heteroatoms, which create problems in terms of emissions that you have to take care of. And then the objective of the upgrading, the lowest objective of upgrading is actually to lower the viscosity and make it move easily. And then lower the density as a higher objective and removal of heteroatoms. So typically, heavy oil or bitumen is sent to an upgrader that would look something like this. It has so many units, including the atmospheric distillation, which is similar to what we have in a normal refinery. And then you take it to vacuum distillation. And then you have an upper cut, which is the lighter oil that you can use, and a lower cut, which is the heavy oil that needs cracking. So you send the heavy oil for cracking, delayed coking, and then cracking, which is a unit that would have a catalyst, high temperature, high pressure. And in order for it to make the oil shorter chains, so it cracks the hydrocarbon chains. So this is one of the objectives of the hydrocracking. The other thing is it takes the heteroatoms. For example, if you have sulfur, you will end up with sulfur H2S, which is hydrogen sulfide. And if you have nitrogen within the heavy oil, you will end up with NH3, which is ammonia, right? And then you crack those heavy chains or high hydrocarbon chains into shorter ones. And those shorter ones are user-friendly. So you can use them in cars, and then you can use them for daily activities as liquid fuel. Now, the environmental impact. So the surface extraction and upgrading, it has a big environmental footprint, and it has its toll on the environment. We all know We have seen some of the pictures from northern Alberta. This is what's happening in Fort McMurray. This is an open pit mining. And you can see also the transportation and the need for removing all that sand into places where it's processed. Again, this is an environmental footprint. And in addition to that, there is the tailings ponds, which are very famous here in Alberta and now becoming famous all over the world, right? And this is a picture for the tailings ponds, this satellite picture in 1974. The same site in 2004. You can see that the size of the tailings ponds is actually increasing, which means that something has to be done. One of the reasons that the size is increasing because we're processing more of the oil sands. The other reason is there is accumulation. So we don't treat the water the way we're supposed to treat it, and that's why it's accumulating. So there is a need for a new technology, new approach in order to minimize or try to at least lower the growth rate of the tailings ponds. And in addition to that, so this is a closer look, on the tailings ponds, and this is the Athabasca River. Not very far from the river, so there is a big risk if there is a spillage or there is a leak or you're actually jeopardizing the environment as a result. And in addition to that, upgrading on the surface also has its toll on the atmosphere and the water resources, right? And on top of all this, that the surface upgrading or surface mining will never provide access to the deep deposits that I showed. There is an overburden layer, and then there is deep deposits. And those deep deposits have most of the bitumen. It's not the surface one. It's the deep deposits. And those actually are accessed currently with the technology that is most widely used in Alberta, which is the SAGD processes or SAGD approach, which is the steam-assisted gravity drainage. And in this approach, you drill two horizontal wells. One of them you use as an injector in which you inject steam. So steam will develop that chamber, if you like, and that chamber would be at a higher pressure than the surrounding and a higher temperature than the surrounding. The most important thing is the temperature. So what happens as a result of increasing the temperature of bitumen is going to flow. It makes its viscosity lower and it's going to flow. You collect it at the bottom, which is the producer well. So you start producing bitumen at the producer well at this point on. Now what happens again, you're still producing bitumen that you need to take to an upgrader on the surface and then upgrade it and make sure that it's working fine and then more used as liquid fuel. So this is again what's happening. So again, I should have showed that while I was talking. So there is the steam that is being injected and the bitumen that's being produced, right? The idea was to couple, the A-size idea was to couple the in-situ recovering using the same platform, SAGD, with actually upgrading. How can we do this? Is we actually distribute an ultra-dispersed catalyst within the formation between the two injector and the producer well, and using the same temperatures of the SAGD process and the same pressures of SAGD process, and by addition also of hydrogen, we can actually make the upgrading, which is the cracking that you've seen in the previous picture, within the formation here. And instead of producing bitumen, we can produce upgraded bitumen, which is easier to flow, more environmentally friendly. If you need to process it, it will be easier to process it using conventional refineries as opposed to the upgraders. And it would have lesser environmental impact, at least on the surface. Now, there is an environmental impact within the reservoir, and this is something that we have looked into, especially my group as opposed to other groups that are working within A-size. I was looking at the environmental impact and reducing the footprint of actually in-situ upgrading, what we call the new method.